All right, folks, I'm going to walk through the three tools for assessing our least square regression model on the calculator with the first period's height and handspan data. You know what? Actually, folks, I'm going to use third period. So because they're very different and their results will be quite different. So you've seen the video that talked about first period's results that went into the fancy note packet. I'm going to just do third period instead. So to do that, I need to pull them up in here. So I'm going to clear what I've got. So you got to clear enter on the title of the name of the list. So list one on the title, clear enter goes away. Cool. So to pull these back up, I go cursor on list one. I have to go second stat to go to list, and I'm looking for third period's heights, not handspans, but heights. And then I'm going to fill list one with it. It says list one will become heights. Yes. With that, same thing for list two. I want to put the cursor on the name of the list I'd like to change. I go to second stat, which is list, and I choose handspan for third period. Okay, and then I'm just going to double check. I'm going to scroll up to the bottom and loop around to the bottom of my list to make sure they're equally long. Cool. So to do this, so I'm going to use three tools for assessing the model: residual plot, typical error, and R-squared, coefficient of determination. Step one, to get a residual plot. Now, this pair of lists, I've done it before, but it's been a while. I just erased stuff. I need to run the least square regression line again to store the residuals in my calculator. So I'm going to go to Stat, Calculate Linear Regression. Your calculator automatically stores your most recent residual values for the last thing you did a linear regression for. So I'm going to pop y1 in here. That was vars, y vars function y1. So it's going to pop up on my graph so I can see it. So I just ran the linear regression. This is in fact third period's height handspan values. And I'm going to have to capture some of these. So let's chop this out. So that's going to be my last tool. So I have three tools: residual plot number one, S is number two, and R squared is number three. R squared is right here, so I'm going to write it down. So I have a 60.6%. All right, so I have the equation. I don't need that again, but now that I just ran the regression, it has stored my residuals. So now what I'm going to do, I'm going to go to, you know what, guys? I'm going to go to Stat. I'm going to go Stat, and I'm going to edit. I'm going to pop the residuals in list three. So on top of list three, I go to second Stat to my list menu, and list residuals are always stored in here, but it's for the very last thing you did a linear regression on. So you have to keep track of whether you've done the thing you currently have. So residuals. I'm going to fill list three with residuals. And a way to check, just kind of look at them. They should be positive and negative, but also if I loop up and around to the bottom of the list, they should be equally long because they belong to this data set. So it's the correct residual. All right, so now I need a residual plot. It's a graph that has list one, so heights as the x values, and instead of having handspans as the y values, it has errors between the actual handspans and the lines predictions. So I'm going to go to stat plot, and I'm going to change this so list one is still doing its thing. That's my x values, the height, but list two is going to be replaced with list three, the residuals. Or if you haven't popped them into your chart, you can actually just choose residuals. So you can go to stat, go to list, second stat, and again, pull residuals out of here. And so then you're doing a residual plot. It literally says residuals when you're graphing. So you're doing heights versus residuals of handspans. So to run this, I'm going to go to Zoom 9, find my stuff. There it is. All right, this looks pretty good. What I'm looking for here is random scatter. That's what the notes say. I would like to see a residual plot with no obvious pattern, no curving up or down, and no fanning. Now to sketch these, this is actually rather challenging. I'm going to trace. Everyone's on here randomly in terms of height and whatnot. Now this is somebody who's towards the far end of my heights. So somebody who's in the tallest, one of the taller people. So what you want when you're sketching these is you want to name each variable and have the maximum and minimum on here. So this is going to be heights. And I just want to have a range on there that matches what the data is doing. And for the residuals, I don't know if I'm going to jump around and see how big they are. So this is somebody who's 73 inches tall, and the line over predicted their hand span by half an inch, right? So I'm gonna jump around. I wanna get a feel for my maximum and minimum heights here so I can label this on my piece of paper. So I'm trying to get to this point maybe and this one. And you are just literally jumping around. Why aren't you tracing? So you're just randomly jumping around. Oh, that's good. I want this one. So this is somebody whose error is quite small, but they have the most negative one. So this is, we're not going to make it past -1, right? And then I kind of want this one. So I'm going to keep scrolling to the right to just go through the entire list on my calculator until I can get a feel for this. Now, if you find this really annoying, you can just look at the list that you put in list 3 and find the largest one. That's fine. But I didn't skip it already. There it is. So this one also not very large. This is great. So not going to make it past 1. So these are residuals of hand spans. They're actually in inches. So are these. So this is great. And then I'm going to sketch this. And folks, I'm not going to be super careful about this. I'm going to be like, okay, short person here, large hand, line under predicted. Next two people, line over predicted their hands. I'm just kind of matching the pattern, but I'm not being super careful about placement. So that's just sort of saying to you that I'm not going to super carefully read your graph when you do this. Don't worry about it. This guy's a little too low. I didn't want to, you know what? Let's go to 0.8 and -0.8. That'll match. Okay. So this is my residual plot. What do I want to say about it? I see the residual plot has a random scatter. And that's exactly what I want. And it indicates that the scatter plot itself is indeed linear. I'm checking if when I wrote this is a strong positive linear relationship between handspan and height, whether that was actually true. So I'm fact checking myself on the linear part. So if I see a random scatter plot, random residual plot, that is a good sign that linear was correct when I said it earlier. So this is a shape check, right? This is just a form check. All right, it's very fussy making it happen on the calculator, but it's important and you'll be asked to do it a fair amount. All right, so that is no concern. Number 2, typical error. How good or bad is my line at predicting stuff? Typical error is S. And for us, the way we're going to get that, so this is going to be your typical residual. And just a heads up, guys, I have residuals listed in list 3. I'm going to run one of our stats on my list 3 to see what the average is. You're going to see it's very, very not helpful. So I'm going to calculate one of our stats for list 3. You can't really do it to residuals. I think it resists. But if you put it in a list, you can do stuff on it. So before you write this ridiculous number down, that's 0, right? That's -9 times 10 to the -14. So our typical error is 0. So typical residual, the mean is 0, and it's always going to be 0, which is why we don't use mean residual as our tool. What we do instead is, since 0 is the mean, we are looking at typical distances from the mean in the positive and negative direction as our way of guessing what a typical value is. So the mean 0, and we're looking at, hey, on average, how far away from the 0 am I? Heads up, guys, that's straight up standard deviation, right? Standard deviation is, on average, how far away from the average are your points? If the average is 0, on average, how far away from your points are you is going to be another way to find a typical residual. So our typical residual is our S, and it says 0.46. This is lovely. All right, so what does this mean? We would like to have, good sign is errors, this is in inches, errors that are 10% of typical Y value or less. That means our line is really good at predicting, and the errors it makes are not huge, and we're not concerned about it. So to do that, I am going to look at our typical height for third period, with our typical hand span for third period. I ended up using it for first period by accident. So first period, our typical value is 7.5, 7.8 for third period. Not a big deal. All right, so I would like to know, is this 10%? So my Y bar my typical handspan is 7.8, and then our typical error, I'm going to divide them. My typical error is 0.46. So 0.46 divided by 7.8. So this is saying, careful with your zeros, folks. This is taping, our typical errors are about 6% error. So we're going to say our least square regression line makes about half-inch error, so 0.46. In handspan prediction. And then we looked at typical handspans and noticed what percent that was. This is only about 6% error. It's less than 10%, which means that that's a pretty great prediction and that I'm happy to use it, right? So least square regression line is useful. Recommend use, right? So I have a good residual plot. It is in fact a linear model. Putting a line on that is a good idea, and my typical error is quite small, so I would recommend using the line. And then the very last tool we have is called the coefficient of determination. Sounds very, very fancy, but it's literally R squared. So it's the coefficient that we use to assess how close or tight the scatter is on your scatter plot squared. What it actually does is it tells you how much better using the line is for your predictions than just using average handspan. That's kind of what it's about. It can be computed in a very, very complicated way, but fundamentally you just take your R and you square it. So using the line is 60% better than not using the line and just guessing the average. That's kind of what's going on here. So we're going to say 60.6% of changes in handspan can be, there's many, many different ways to phrase this. Pick one you like. Attributed to, the one that usually sticks out for me. Explained by works too. Or accounted for. And then the way the sentence continues, you also have some options. Can be accounted for sort of changes in height. So if you notice that somebody's handspan is bigger than somebody else's, and you look at their heights, and you can say 60% of the time, just knowing somebody's height helps you explain why somebody's handspan is changing. So yeah, I would say pick one of those three, attributed to, explained by, accounted for, by changes in height. The other option is you can say the least square regression line itself, model predicting height. So basically we're saying if you're trying to guess somebody's handspan, pretty sure the line itself or knowing someone's height is helping you understand why handspan is changing 60.6%. It does mean that we're missing some explanations. So let's just take a moment to write that down. We're missing 29.4% of the explanation for handspan changes are missing. So we're missing 24.9% of our explanation. Maybe need to find some more variables, right? Now, maybe those other variables are several different things we mentioned. Hand dexterity being a function of whether somebody's playing sports, where their hands have to be large to grab things or hold on to things. Maybe it has to do with playing the piano or other instruments, right? Those could pile up and account for the changes that we're seeing. All right? And that one you just get from the R squared when you run the linear regression.